everyone. We're going to work on limit laws today. So our goal is to move from the numerical approximation technique, which is very time-consuming, towards a more algebraic technique. In order to achieve an algebraic method of finding limits, we're going to need some limit laws. So we have here a list of a few basic rules that allow us to break down more complicated functions into simple ones that we already discussed. So we've already discussed the constant function and the identity function. So our goal here is to take these more complicated functions and get them down to those. So let's just review very briefly. If we have the limit as x approaches c for a constant function, let's just say our constant is k. Okay? So meaning our function, no matter what you plug in, you're always going to get the same answer, k. So in this case, the answer will always be k for the limit. No matter what x is doing, it doesn't matter. The function always gives the value k. The other one that we've talked about is the identity function. So if x approaches c, and the function is just x itself, the answer will always be what you are approaching, c. These are the two things we're going to try and get to using these limit laws. Now, there are a lot of laws here, so what I'm going to do is I'm actually going to do examples, and I'll come back and show you which laws we're going to apply. So, the first example, there it is. So here we have a polynomial, and we are going to try and use our limit laws to break this down to either just limit of x or limit of a number, a constant. That's our goal. So, if we look at this, we should be able to see a couple different things happening that we can go back and use our limit laws to help break down. So, all right, keep this problem in your mind. Let's go back to our limit laws and look at it. So in our limit laws, we have limit of a sum, limit of a difference. We have a constant inside of our limit. We have limit of a product, limit of a quotient, limit involving a power on a function, and limit involving root on a function. Those are all the different things we're looking for, and each one of those we're able to break up, and I'm going to show you how, using these laws. So in our problem, we have a polynomial. In our polynomial, we have a sum, a difference, and a power, and a constant in front. So let me show you how we're going to work this out. So first of all, the most basic step that we can do when we are working at a limit is to break up into individual terms. So instead of looking at this as one big limit function, what we're going to do is we're going to apply the sum and the difference rules. What those rules do is they allow us to take the limit of each term separately. So we're going to have the limit as x approaches c for our first term, x to the fourth. And then we have a minus sign, so that's our difference law. Let me go back and show you the difference law. The difference law says if you have a minus sign, a difference inside of your limit, you can break that up, and instead of finding the difference and then the limit, it says you find the limit of the first piece of the function, find the limit of the second piece of the function, and subtract the limits. So instead of doing subtraction first, you find the limit first, and then subtract. So the way we write that is like so. We take the limit and we put it on each term separately. So limit of x to the fourth minus the limit as x approaches c for 3x squared. So see how now the limit is on each individual piece. We find the individual limits and then we subtract the answers. We do the same thing for the last term, except this time it's an addition. So we're using the sum rule for breaking up the limits. So the sum of the limit as x approaches c for the last term is just a 1. This last term is one of our goals. What do you see there? We're taking the limit of 1. What would that be? What kind of function is just a 1? This is a constant function. This is one that we've already discussed, and we already know the limit of a constant is the constant itself. So that one we can actually find the answer to. The other two, we still have some work to do. So let's see, what's going on in this one here? X to the fourth. We're almost down to just the identity function of x, except we have that fourth power. Well, did we have a limit rule that allows us to do something to that power? Let's go look. So let's see, we go down our list. I see a power rule, number 6. What does that say we can do? Well, let's look at it. The power rule says if you have a function and a power on it, that power can be taken outside of the limit, or you can think of it as the limit being brought inside of the power. So what they've done here is they found the limit of what's inside and then put the power on top of that. How do we write that? Let me go to a new line. So we're going to take the limit as x approaches c of what's inside the power. Okay, so we're bringing the limit inside the power. Now the power is on the outside of that. Cool. This inside here is the limit of an identity function. That is one that we've been talking about already. So if you missed that video, go back and watch it. It's very important. So this is an identity function. What's the limit of identity function? Whatever you're trying to approach. So as x approaches c, well, that's going to be your limit, c. All right, so we're almost done. We have the first one figured out, and we have the last one figured out. We need to work on the middle. So what's going on in this middle one? There's actually two things going on. We have a 3, which is a constant multiple. And we have power. Well, we know how to deal with the power function. The power, we just did that. However, we have two things going on. Which one should we do first? If I bring the limit inside and put the power on everything, that means the power is going to be on the 3 as well. So we can't do power first. First, we have to take care of that 3. Let's go back to our limit laws and see which one allows us to deal with a constant multiple. Oh, there it is, number 3. What does it say? It says if you have a constant inside of your limit, just take the limit of everything else and multiply by that constant after you take the limit. So the limit can bypass the constant, or you can think about it as the constant can come out of the limit. So what we're going to do is we're going to bring the constant outside of the limit. So 3 comes out, and we take the limit of what's inside. But we've already dealt with this, haven't we? The limit of x squared. What do we do with the square? Oh yeah, we do the limit of x and then square that. So I'm just going to put parentheses here and put the square on the outside of the limit. So we're going to take the limit of the x and then square it. And now you're ready, because this inside here is also an identity function. So if we let x approach c, well, the limit of x as x approaches c is c. Don't forget that power. All of that other stuff still has to come down. Minus, we have a 3. So the 3 is just going to chill out. We're going to take the limit. So the limit as x approaches c for x, well, let's see. If x goes to c, then x has to go to c. Don't forget your square is on that limit. Plus, what is the limit of a constant? Well, it's always going to be 1, so the limit is going to be 1. The function always equals 1. The limit will also equal 1. And there you go. If c were a number, you'd use your number instead of c, but this is an example of how the limit laws allow you to take a more complicated function and break it down to things that you know. Identity and constant functions. I think it's cool. Alright, let me show you another one. So here we are dealing with two polynomials, but in between those we have a quotient. We have a fraction. So let's go back to the limit laws. See what the limit laws say we can do when we have a quotient. Looks like it is number 5. Number 5 says, if you have the limit of a quotient, take the limit of the top, take the limit of the bottom, and then divide the two answers. So instead of working one big problem, you're going to break it up. You're going to work the top, and you're going to work the bottom each separately. Note, the bottom limit cannot be 0. The bottom limit is 0. This will not work. You're going to need another tool that we're going to talk about later. But as long as it works, good. Alright, so, like I said, you're not going to work it as one big quotient. You're going to work it as a top and a bottom. Right? Now, these two used to be said, wait a second, these are just polynomials. That's just like the last problem we did. All we have to do is do each term separately, and then bring the powers outside of the limits. So it's going to look something like, let me go to a new line, this might be a little big. So we're going to end up with the limit as x approaches c for the first term is an x, and we're going to put the power on the outside. Plus, we're going to take the limit as x approaches c for, let's see, we have x squared. So we have an x, where we take the limit up, and the square we put on the outside. So we've used the sum law for limits, we've used the power law, and then finally one last term, minus, we just take the limit as x approaches c, or 1, a constant. So we use the difference law to pull that, separate that term out from the others. Each of these that we have here is one that we memorized. So these two here are identity functions, and this last one is a constant function. All of these we already talked about how to work these out. All right, so on the bottom we do the same thing. We're going to have the limit of the first term, x. The square will go on the outside of the limit, minus the limit as x approaches c for the constant 4. Again, these are all things we've talked about. We have, first of all, right here we have a constant, and here we have an identity. So, what do these all become? The identities are all going to be whatever x is approaching. So these all become c, because x is approaching c. The constant functions are just going to be whatever the constant is. So limit of 1 as x approaches c is 1. The limit of 4 as x approaches c is 4. If we write this out nice and neat, don't forget your powers. So we have c cubed plus c squared minus 1 over c squared minus 4. If c were a number, you plug in your number instead. That means in general. There you go. So that's 2 examples. Let me do one more example with you, because we haven't talked about the root law yet. All right, so let's go back to our limit laws. We have the root rule right here, the last one. Now the root rule is important because, it's important to do this one separately. It has a couple extra little things. Number 1, in your root must be a positive number. If it's a negative number, then you're going to have to deal with that negative separately before you come and use the root rule. Also, it's in the parentheses here. If n is even, like square root, 4th root, 6th root, if n is even, the inside must be positive or 0 for all x's around your c that you're trying to approach. If not, you'd be taking the square root or a 4th root or a 6th root of a negative number, and that's undefined. So in order to be able to take the limit involving an even root, you must be dealing with positive numbers around the x value that you're approaching. It's not the x value that has to be positive. In this case, I'm showing you actually an x value that's negative. It's the answers. So as x approaches -2, all of those x values, when you plug them in, they must give you positive values inside of the root. X itself can be negative, because here we're squaring it. When we square an x, it becomes positive. So that's not a problem, in this case, to have a negative x value. So what does the root rule say, though? Let me go back to it one more time. The root rule says, if you have the limit involving a root, take the limit of the inside and then put the root on. So the root is on the L. So L is the limit of the inside, and then we take the root afterwards. So we're going to take the root afterwards. The limit moves inside of our root. So we're taking the limit of this. The limit of the parentheses, that's a polynomial. We've already worked with that. We break it up. So we're going to have the root of the limit as x approaches -2 for 3x squared minus, using the difference rule here, the limit as x approaches -2 for 1. This guy here at the end, he's a constant function, so we're good to go. We don't have to simplify that anymore. The other one has a constant multiple. So what does the constant multiple rule say we do when we're trying to take a limit? The constant comes out of the limit, so it should be in front. And then all we have left to deal with is the power. So let's rewrite it. The root's still on the outside. We put the 3 in the front, so we have the limit as x approaches -2 for x, and then the square goes outside of the limit, minus the limit as x approaches -2 for 1. Now, we actually have a value this time, so we can actually evaluate this. So, for a identity function, what is the limit of x as x approaches -2? Remember, for identity functions, if you want to know what x is doing, do what x is doing. So it says x is approaching -2, so the limit of x has to be approaching -2. That's what the box is going to be. Over here, identity. If the function is always 1, the limit is also going to be 1. So our square root, inside we have 3 times a -2, don't forget to square it, very common mistake, minus the limit as x approaches -2 of 1, we already said 1. Work it out and you're done. Square root, let's see, 3 times negative, alright, so let's do a square first. So -2 squared would be positive 4. So 3 times 4 is 12, minus 1, that gives us the square root of 11. So this here is the limit of our original problem, which was, I got right there. Alright, so in this video we've reviewed the limit laws, and we've showed you how you can take a much more complicated function, break it down using the laws into the most basic possible of identity and constant. In the next video, you're going to learn how to approach these laws in a more quick, a quicker fashion, because we're going to have a special theorem to go along with them.